Okay, dear student, let me solve this problem from the tutorial. So here, uh, this ball C strikes at this ball B, and ball A and B are connected by a string, and initially the string is slack, and of course when the C strikes B, B will get some velocity, and after some time it will reach to the position shown over here, and this string will become taut. So the question over here is velocity of each sphere immediately after the chord becomes taut. So first of all, we have to solve this problem into two steps. First, the block C or the mass C strikes B. So there is exchange of some velocity or momentum that let us look first. Let us take care of first. So when this block C strikes B, so initially it is having V naught velocity and V is 0 for B, and after impact this C will be having some velocity, let me call it V1, and this B will be having some velocity V2. So here when you write impulse as linear momentum L1 in the direction of x, let me call this as x direction, this can be written as m times v naught, and here the linear momentum in x direction can be m times v1 plus m times v2. Both are the having mass of m. So what I get, linear momentum balance or conservation, it gives me mv naught is equals to mv1 plus mv2, or you can say v naught is equals to v1 plus v2. Another thing is told that assuming perfectly elastic impact between B and C. So when there is an elastic impact between B and C, it means that so whenever you write E is equals to, coefficient of restitution is 1, this imply V naught minus 0, V2 minus V1 is equals to E times V naught minus 0, and this will give you V2 is equals to V naught plus V1. So from this equation and from this equation, what you can get is that V1 is equals to 0 and V2 is equals to V naught. Now in the second step, what you can look into, so initially this is B and it is connected to A, this is having v2 velocity, and after string become taut, this is A and this is B. Okay, and the dimensions have been given that this is L and this is L by 2. So since when the string is taut, see, after the string becomes taut, velocity would be having B would be having some velocity in arbitrary direction, so it will have two components. Similarly, velocity of A would be having two components. For the sake of simplicity, let me take the directions. Instead of taking in x and y direction, let me take this direction as n, this direction at t and this direction as n. So if this angle is theta, this angle would be theta. So here also, in case of velocity v2, this is n direction and this is t direction. So n is the perpendicular to the string, taut string, and t is in the direction. So the velocity of B would be, so A would be having a velocity of this tangential direction and Vn of A. Similarly, string B would be the B would be having velocity Vn of B, and this direction the velocity would be velocity in tangential direction. So the reason why I am writing this Vt and this Vt same, so the normal direction velocity of A and B are different, maybe different, but the tangential direction velocity will always be same of both the blocks. That is the only condition for the string to be taut. If the velocity of A and B in the tangential direction or in the direction of a string are not same, then this string will no longer be taut. Since we are analyzing of the for the taut string case, so we have one variable here Vt and two variables Vn A and Vn B. Now when you apply the linear momentum in n and t direction, so in here linear momentum in n direction you have to write and linear momentum in t direction you have to write. So linear momentum in n direction will become m v2 and cos 30. Basically this becomes 30, theta is equals to 30. You can work in terms of cos theta, and lt would be m v2 sine 30. So here I have taken that this is for this block only, since this is at rest. Similarly, here ln can be written as m into Vnb plus m into Vna, and tangential direction can be written as 2m times Vt. So when you equate these two, and this will give you Vt is equals to V2 sine 30 by 2. Similarly, this will give you V2 cos 30 is equals to VNB plus VNA. So again, since we have three unknowns, of course there are this 1, 2 and 3 unknowns. So what we need one more equation. So let us take the angular momentum about point A. So this is V2, the angular momentum just before the string becomes start. So it would be, so let me redraw. A and B. This is going with V2 and this is L. This distance is L cos 30. So angular momentum H about A would become L cos 30 times mv2, and after this become taut, this is Vn B, this is Vn A, this is Vt, this is also going with Vt. So here angular momentum can be written as m Vn B times L. So when you equate these two, this will give you Vnb is equals to V2 cos 30. Since earlier we also get this expression, so when you equate this and this, when you use these two equations, you can get Vna is equals to 0. Okay, so this become V0 root 3 by 2, and this become Vt is equals to V0 by 4. Now the next question in the problem is that the fraction of kinetic energy of the system which is dissipated. So let me write the kinetic energy, initial kinetic energy will be half m V0 square, and final kinetic energy half mass of B Vnb square plus Vt square plus half mass of A Vt square. Of course, since plus half mass of C Vc square, which is 0, right? So when you write these expressions, you will get half m, and Vnb become V0 root 3 by 2, it becomes V0 square 3 by 4, V0 square 3 by 4 plus Vt becomes V0 by 4, so you will get V0 square by 4 plus half m V0 square by 4. So when we take half m V0 square 3 by 4, oh sorry, this become 4 square 16 and 16, so it become 1 by 8. and finally half m v naught square 7 by 8. So the energy loss can be half m v naught square minus half m v naught square 7 by 8 half m v naught square, which is becomes 1 by 8. This is the fractional loss of the energy. Thank you.